Hi everyone. Welcome to the stream today, and let me just quickly check the audio levels and make sure that uh, you can hear me, and then we'll start. All right. Quickly check the audio levels. Yeah, everything looks good. Okay, so let's start. There's some people in the chat as well. All right, so this is the review for the last test, and the last test is going to be either Thursday or Friday, depending on what section you're in. And I've already written it for the Physics 112. I think it's 39 questions, and for the Physics 102, it's 41 questions. Okay, and it's going to cover not all of electricity. There was that preliminary part of electricity on Coulomb's law. We already tested that in test 2. We're just going to do voltage, current, resistance, and capacitance, basically circuits with those components in it, and magnetism, and then finally optics. Okay, and let me see how many questions I have today. I think I have 9 questions for everyone, and then a series of questions just for the calc-based physics students. Okay, so let's start. So the first question is a typical question where I give you a circuit. This is like in your one assignment on this. And I've got some resistors either in series or in parallel. Now I only have 2 here, but you could expect to see maybe 3 on the test. And 4 is a little bit much, but there's a possibility of either 2 or 3. And I'll ask questions like this. I'll ask, what's the total resistance of this circuit? What's the total current through the circuit? What's the total power dissipated by the circuit? Remember Joule heating, because resistors will convert the electrical energy into heat. And what's the voltage drop across each resistor, and the current through each resistor. Okay, so let's start off with the first one. So what's the total resistance? And the first thing you need to identify is you have 2 resistors here, and they are in series. And resistors in series, the total resistance, you can see the word total or effective. I use total, effective, or equivalent. They all mean roughly the same thing. So the total resistance is going to be R1 plus R2 for that. Okay, and in series they will just add. All right, and here in this case that's going to be 3 plus, it's kind of obvious, 3 plus 7 kilo ohms for a total of 10 kilo ohms. Okay, so that answers our first question. The entire circuit, let me push that down there. The entire circuit has an effective resistance or a total resistance of 10 kilo ohms. Okay, so again in series they will add like that. All right. Let's take a look here in the chat. Oh, some more people joined. Okay, good. All right, now that's question number A. B is what's the total current? Now, if you have the total resistance and you have the total voltage across all of it, and you'll see here I didn't say what the voltage was in the body of the question, but you can see here that one end is at a 10 volt. You can even say plus 10 volts like that. Okay, so one end is at plus 10 volts, the other end is at 0. Okay, so the total voltage across both resistors is 10 volts. You could write something like V total is equal to 10 volts like that. It's not the voltage across the 3 kilo ohm, it's not the voltage across the 7, it's the voltage across both of them, so it's like a total. And you say, well, is there a relationship between current, which is what I'm asking for, and R and V? And the answer is yes. And this is Ohm's law. V is equal to IR. Now, this Ohm's law can be applied to the entire circuit, or it can be applied to individual resistors. Okay, and we'll see that as we go along. So watch it. This is it looks like a simple equation, but because you can apply it either locally or you can apply it globally, it can tell you a lot about what's going on with the circuit. Okay, so in this case, I'm asking for the total current here, so I guess I could put a little subscript total there. And to do that, you use the total resistance and the total voltage. All right, so I made the numbers easy on purpose. So you've got 10 volts here for the total voltage. That's going to equal your total current. And the total resistance is 10 kilo ohms. Let me put this in. Whoops, 10 kilo ohms like this. All right. And nothing tricky here, except you got to watch it that K is really 1,000. So this is actually going to be 10,000 ohms. and now it's an MKS, and so the total current will equal the 10 volts divided by the 10,000 ohms, and that number is actually going to turn out to be, just 0.0001, all right, because you're going to move the decimal over 1, 2, 3, 4, 1, 2, 3, 4. Whoops, I've got one too many zeros like that, and that's in amps, okay? Or on the test, I would convert that to milliamps, and so that would equal 1 milliamp, like that, okay? Now, if you're good with metric prefixes, you could probably jump directly to that without having to put in all the zeros there. If you write this, like that, and instead of that, you put a K there, like that, okay? Notice that this K is in the denominator, so that's 1,000 in the denominator is 1,000th in the numerator, and so 10 divided by 10 is 1. A K in the denominator is a milli in the numerator times an amp, like that, okay? So I don't know if I've ever shown you that before, but that's just another way that you can reason through this, and it just avoids, you know, having to put in a bunch of zeros there. Okay, so total resistance, total current. What about the total power? So the power dissipated by the circuit, total, again, why total? Why do I emphasize that? Because there's going to be a certain amount of heat dissipated by one resistor, and there's a certain amount of heat dissipated by the other resistor, and I want the total heat dissipated by both resistors, okay? So that's why I put the word total there. You know what? We could actually just show you that you could calculate the individual ones, and you'll still get, when you add them together, you get the same answer. So what is that? Well, it's basically equal to V times I, okay? And again, we're doing a total voltage and total current, like that. And the voltage across them is 10 volts. And the current we just found to be 1 milliamp, like that. And so that's going to equal. So, I mean, you could again put in the zeros there and write that as 0.001 amps. Or you could just say, well, 10 times 1 is going to be 10. Okay. A volt times an amp, well, that's a unit of power. And power is watts, okay? But you also have that milli in there, which is just 1,000th, and so it's 10 milliwatts, and that's the answer, okay? So I hope I didn't go too fast there. I just didn't want to convert that. But, you know, if you have some difficulties converting, you know, you could just write this, take out the milli there, and write that as 0.001 amps, like that. Well, if you multiply that, this is going to equal 0.01 amps, and 0.01 amps is 10 milliamp, sorry, not amps, watts, right there. 0.01 watts, and 0.01 watts is the same as 10 milliwatts. Okay, so I'll do the individual powers, even though I didn't ask it in the question. I'll do the individual powers in just a second. Okay, all right, so we got the total power. And the next thing I'm going to ask is, what's the voltage drop across each resistor? This is where it starts to get interesting. And what's the current through each resistor? In fact, I should probably switch the order of these two questions. Let's ask the question, what's the current through each resistor? Okay. And the circuit, because it's in series, there's no splitting of the current. Okay, so think of the current as just like flowing water, something like that. It's flowing electrons. And, you know, they're flowing here along the wire, okay? They get to the resistor and they'll go through the resistor, all right? And nothing is split, you know, it's the same current goes through the other resistor, same current, all the way through. So the current is the same all the way through. In other words, the current through the 3 kilo ohm resistor is the same as the total current, right there, okay? And the current through the 7 kilo ohm resistor is also 1 milliamp, okay? So because there's no split in the wire, you'll see that in the next question. So down here, you see in the next question, you see I have a split there and a split there, and we'll go through that one in a minute. But because there's no split, the total current traveling through any one piece of the wire is the total current everywhere in the wire, and we found that to be 1 milliamp, okay? And so to answer the question, the current through the 3 kilo ohm is 1 milliamp, and the current through the 7 kilo ohm is also 1 milliamp. All right. So that answers question E. But if we go back and we ask now, what's the voltage drop across each resistor? Remember here I was saying, well, you know what, I got to be careful because, you know, there's a difference between applying Ohm's law globally or locally. Well, now let's apply it locally. In other words, let's apply it one resistor at a time. So let's apply it to this resistor here. And you know what, we should give it a name. Let's call this one R1. And let's call that R2, just so I have some subscripts to differentiate the two. So the total voltage across R1 is the total current through R1 multiplied by R1, like that. Okay? And so, well, we just said that the current through R1 is 1 milliamp. So there we go. That's 1 milliamp, like that. And the resistance is, for R1, is 3 kilo ohms, like that. Okay. And you know what? Let me get rid of those underscores just to keep the notation consistent. So V1, the voltage drop across R1, is I1 times R1. Okay. And that's going to equal 1 milliamp multiplied by 3 kilo ohms. All right. And the milli is 1,000th. And the kilo is 1,000, and so they kind of cancel one another, okay? And so what you get is basically 3, and the units would be amps times ohms, and you go, well, what's an amp times an ohm? That's a volt. So that's equal to 3 volts, okay? So the voltage drop across the 3 kilo ohm is 3 volts, all right? Now, you actually don't even have to calculate the other one. We will, but you don't have to, because you know that the total drop is 10. The drop across R1 is 3, so the drop across R2 has to be 7 to make up so that they both together add up to 10. But, you know, if you just do it, just do the calculation here. Instead of V1, you've got V2. That's going to be I2 times R2. Well, I2 and I1 are the same, and they're still the 1 milliamp. R2 now is 7. Okay. And that gives you 7 volts. All right. And so basically what we're seeing here is the drop across R1 is 3, the drop across R2 is 7. So if we just trace it, drop across there is 3, plus another 7 gives you the total 10, and you can see that it worked out consistently. Okay, so you know, I didn't ask, well, I can just add it here. What's the power dissipated by each resistor? Okay, like that. And you say, well, how would I do that? Well, it's the same formula. P is equal to V times I, but now it's not going to be the total. You're not going to do it for the total. You're just going to do it for P1 and for R1, in other words, and you'll do it for R2 as well. Okay, so over here, V1 is the voltage drop across R1, that's 3. And the current is 1 milliamp, like that. And that gives you 3 milliwatts. Okay, so a volt times an amp is a watt. And that gives you 3 milliwatts. Well, it's pretty obvious what the other one's going to give you. This is going to be 7 instead of 3, because the voltage drop across R2 is 7, and so that'll give you 7 milliwatts. If you add 3 milliwatts and 7 milliwatts together, guess what you get? You get the 10 milliwatts total. Okay, so I just did that to show you that everything was consistent. Okay, so there you go. There's the first question. I intentionally made it easy because I didn't want to get lost on all the numerics in solving this. Rather, I want you to see very intuitively what's going on in resistors that are in series. Okay, let me take a look in the chat, see if there's any questions. Okay, oh, it looks like we've got 7 viewers right now. Okay, so there's the story with resistors in series. What's the story with resistors in parallel? Okay, so it's a little hard for me to do an ASCII diagram of parallel, and you see you know, with these text editors, you know, my lines here, they're either too far one way or the other way, but you know, I mean, I think it's pretty obvious that what's happening here is you come up to here, and then at this point right here you get a split. Okay, so with parallel resistors, you're going to have the current splitting. You didn't have that with the series, but you have that with the parallel. Okay, and then it, the current splits here. Part of the current goes through the 3 kilo ohm, and another part of the current goes through the 7 kilo ohm. Okay, and I'm going to ask the same questions. Find the total resistance, find the total current, and so on. Okay, so let's start off here. What's the total resistance? All right. So for this one, the total resistance, just remember that in series they add, but in parallel the reciprocals add. So it's 1 over R total is equal to 1 over R1 divided by 1 divided by R2. Okay, like that. Okay, so it's the reciprocals that add. And so what's this going to equal? This is going to be 1/3 or 1 over 3 kilo ohms. All right, we can work in kilo ohms and then the answer will come out in kilo ohms. Okay, plus 1 divided by 7 kilo ohms. All right, and that isn't our total. That's the reciprocal of our total. Let me work out what that is. So it's 3 plus 7 reciprocal. So this number here, I'll give you a lot of digits. Okay, there you go. And then to get our total, you take the reciprocal of this number right here. Okay, and that will equal 2.1. There you go, 2.1. And since we worked in kilo ohms, the answer is in kilo ohms. Okay, and that's the total resistance. Now, just so you know that you're heading in the right direction, expect that the total resistance in parallel is less than either one of them. Okay, so 3 is the smallest that you have here. The total is going to have to be even smaller. And the reason is that this extra resistor here actually makes life easier for the current, because the current gets to here and it's not forced to go through the 3 kilo ohm. It actually, some of the current can actually split off, okay? And that relieves some of the, you could call it electrical pressure, if you like, through the 3 kilo ohm, okay? And so that's why effectively the two together actually reduce the resistance. All right, so there's the total resistance of that circuit. Okay, now what? Well, now what it asks for next, the total current. Okay, so the total current, same formula, namely Ohm's law, but now you're going to be using for your total resistance the effective resistance of 2.1 kilo ohms. Okay, so the total voltage is 10 volts. All right, and the total current is what we're trying to solve for, and the resistance is 2.1 kilo ohms, like that. Okay, so I total is equal to 10 divided by 2.1 kilo ohms. Now we can do the same thing we did before. That K, which means 1,000, it's in the denominator, so that's like 1,000th. So you could actually write this like separate it out like this. I don't know if this helps, but let me do this. So let's take that K out of there. And you see that K, because it was in the denominator, it's going to give you a milli in the numerator. Okay, and oops, I forgot the voltage there. All right, and a volt divided by an ohm is an amp. Okay, so what is that equal to? So it's 10 divided by 2.1, and that gives me this number right here. Oops. There we go. All right, and let me round it off. That's too many digits. Okay, and that would be in milliamps, like that. All right. So that M out there kind of looks funny, but all I wanted to do was to just show you that the kilo in the denominator gives you the milli in the numerator, and there it is in front of the amps. Okay, so that's the answer right there, 4.76 milliamps. Okay. Great. Now what? Well, I think the next one was the power. Yeah, the total power. All right, and the total power, same formula as above. Where was it? Here it is. So basically, let me get rid of the subscripts. It just might be a little easier to see it. Okay, I mean the subscripts are important so that you know that you're applying it to the whole circuit. But you might want to just memorize Ohm's law as V is equal to IR. Okay, and then add subscripts to say, am I doing this globally or am I doing it locally? Okay, and then for power, it's P is equal to VI. And again, add subscripts to say, do I want this just done locally on individual resistors, or do I want it done for a whole circuit? Well, in this case, let me get rid of that. Okay, in this case, we wanted it total, so we'll just put a total there, and a total there like that. Okay, so the total voltage is still 10 volts across all the resistors, and the total current we just calculated to be that. Okay, and so we're going to have the milli will go out, and we'll just go through, and a volt times an amp. A volt times an amp is a watt, like that. And remember, a watt is a joule per second. Okay, and then of course 10 times 4.76 is 47.6 milliwatts. Okay, and that answers the question, how much energy is, how much power is dissipated by this circuit. Okay, so basically this is 47.6 millijoules of energy are going to be converted into heat every second. All right. Okay, great. What did I ask for next? The voltage drop across each resistor. So this is what's a little tricky. And let's go back to the series circuit for just a second. So for the series circuit here, when you trace it, when you walk from the 10 to the 0 there, okay, you have to go from a potential height of 10. And you can actually think of it metaphorically as being like a pie, okay, like on top of a hill. Now you're on top of a hill, and then you walk down here 3 volts, okay, and then you walk down another 7 volts to get down to 0. Okay, so think of volts as like a meter in height or something like that, just as an analogy. So you start at 10, you drop through 3, and now you're at 7, and then you drop another 7 to get down to 0. Okay, over here with the parallel circuit, it's a little counterintuitive, because you start at 10 and you see you've got 2 paths downhill. You can either go across the 3 and then totally bypass the 7, or you can go to the junction and then travel across the 7 and then get down to 0. So both of these resistors, they start at the top here at 10 and they get down to 0 here like that. So the voltage drop across the 3 kilo ohm is 10, and the voltage drop across the 7 kilo ohm is also 10. And so this is a little counterintuitive, but it's precisely this, because you think of it, I'm at a height of 10 here, and as long as you're walking along the wire, you're not dropping, okay? And so everything that you see there highlighted in blue, that's at 10 volts. From the other side, everything highlighted in blue is 0 volts. And so from the one side of the resistor to the other side of the resistor, you have to go from 10 down to 0. So that's a potential drop across the 3 kilo ohm resistor of 10 volts. Well, it's the same story with the 7. Okay, I know you have to go through the junction here. Whoops, like this. I have to walk through there. But when you're over here, you're at 10 volts. If you trace it the other way like that, you're at 0. So even for the 7, you start off at 10 and it drops to 0. So just be aware of that difference between how the voltage drop works for series and parallel. And so let's just say here, the voltage drop across both the 3 kilo ohm and 7 kilo ohm resistor is 10 volts. Okay, so well, that answers that question. Both of them have a 10 volt drop across them. Okay, now that's the voltage drop across each resistor. What's the current through each resistor? So unlike the series, let's go back to the series, the voltage never splits, and so the current never splits. So the current through the 3 kilo ohm and the current through the 7 kilo ohm have to be the same. Okay, you can see my blue highlighting there, it's the same right across. But with parallel, you get the split, and the split occurs right there. Okay, so some of the current's going to go one way, some of the current's going to go the other way. All right, now we have we can calculate we did calculate the total current there like that, but that total current is the total current through the combined 2 resistors. It's not the current through one resistor or the other. If we add the current through both of the resistors, it should add to that. But that isn't the current through either one or the other. Okay, so let's do it. You say, well, all right, fine. How do I calculate the current through that resistor there? Well, it's Ohm's law once again, but this time it's going to be through resistor 1. Okay. The voltage drop across resistor 1 we said was 10 volts. Let's do it on the next line here. 10 volts like that. The current through resistor 1, that's what we're trying to calculate. And resistor 1 is 3 kilo ohms, like that. All right. So this tells me that I1 is going to equal 10 divided by 3. Oops. Oh, it's 3.333333. Okay. So let me grab a bunch of digits here like that. I didn't need a calculator for that, but and again, the K is in the denominator, so that's going to be milliamps. Okay. Same thing now, but for number 2, resistor 2, and so that's going to look like this. Okay. It's going to be I2, and it's 7, not 3. And so I2 is going to equal 7 reciprocal. What's that equal to? There it is. Okay, like that. And that's actually a 3 there, like that. Milliamps. All right. I think that I did that right. 10 divided by 7. No, I did it wrong. Sorry, guys. One sec. It didn't look right. Yeah, I don't know what I did there. It's I'm off by a factor of 10. That's all. There it is. Okay, great. Okay, so let's take a look at what I'm saying here. The current through the 3 kilo ohm resistor is 3.333 milliamps. Okay, so through there we get the 3.33 milliamps, and through the 7 kilo ohm resistor it's going to only be 1.43. Does that make sense? Yeah, because the smaller the resistor, the more current is going to go through there. So you're going to get the 3.33 there and the 1.42 through there, like that. Okay, 1.43. Now, if I were to add those two currents together, because the current is coming in here and it splits. Okay, now whatever current is going through one plus the current that's going through the other, that current had to come directly out of the 10-volt battery. And so if we add those two together, this number here plus that number there, we should get, and let me check it out, we should get the total current, which we already calculated. And it's this, milliamps. And is that what we just calculated above? Well, we round it off. Okay, so if I round off here like that, take one of the 3's out of there like that, round it off to just 3 significant figures, I find that the current through both of them together, the combined current, is going to be 4.76 milliamps, and that's what we calculated above there like that. Okay, and the reason I did this is I just wanted to show you that this whole thing is consistent. Okay, so whether you get the total current by applying Ohm's law globally, or you get the total current by applying Ohm's law locally and then adding, you're going to get the same answer. Okay, so was there another question? The power dissipated through each resistor. That's boring. I think I'll skip that, because you'll get each power, and when you add them together, you're going to get the total of 10 milliamps. I don't think it's really worth it. But you just do V1 I1 and for one of them, and then V2 I2 for the other one, and add them together, and that's it. Okay, let's see if there's any questions in the chat. Nope, no questions. So I assume everyone's doing okay. All right, so there's the story with resistors. What's the story with capacitors? Okay, so I didn't want to make the stream too long, and you can always go back and watch my earlier streams, or even the pre-recorded lectures on how to do these. So I didn't want to burden you with too many similar questions. Okay, so I kind of prefer to do a simple one right now that just brings out the intuition as to how resistors work in a circuit and capacitors work in a circuit. So let's take a look at the the capacitors in a circuit, and if you want to see a more complicated problem, go back to those previous streams. Okay, so in this case, I want the total capacitance, total charge on each capacitor, and voltage drop across each resistor. Okay, let me just do this. All right. So first, let me remind you how a capacitor works. So with a capacitor, when you apply a potential, a voltage across the capacitor, it charges up. Okay. Now the capacitor actually has a space. You can think of it as two parallel plates, and there's actually a space in between. Okay. And so the electrons can't jump from one side of the capacitor to the other. But because there's a potential, the electrons are being squished onto one side, and electrons are being sucked away from the other side, making one plate positive, one plate negative, and one plate positive. And they're happy that way. They like negatives and positives, like being near one another. But you can't put an infinite amount of charge on one plate. You'd blow the plate apart. Okay, if it were all negatives, because eventually the number of negatives on the plate will want to get away from one another more than they are attracted to the positive plate. Okay, and so at that point, you just can't get any more charge. But you can always try to force more charge. So the bigger your voltage that you put on the capacitor, the more charge you get. And capacitance is then defined as C is equal to Q divided by V. Okay, so this is kind of the equivalent of Ohm's law, but for capacitors. All right, so the capacitance, that is how much a capacitor is able to store charge, is equal to how much charge do you get per volt. Okay, how much charge do you get per volt. All right, so here we have two capacitors in series. Let me get rid of that because we don't need that. Okay, we have two capacitors for series, and I asked for the total capacitance. Capacitors, they actually, let me take that space out of there. Capacitors actually work the opposite of compared to resistors when you go to combine them. Okay, so for resistors, just to remind you, resistors in series, they just add. Okay, so for resistors in series, you just add them to get the total. But for capacitors in series, you actually add the reciprocals. So 1 divided by C total is going to equal 1 divided by C1 plus 1 divided by C2, like that. And maybe we should just name these. Let's call this one C1, and this one is C2, like that. Okay? All right, so let me just substitute in here. I get 1 divided by 3 microfarads plus 1 divided by 7 microfarads, like that. Okay, and that's going to work out to 3 reciprocal plus 7 reciprocal. That's going to equal this number right here. Okay, and then when you take the reciprocal of that, because remember, that's not C total, that's 1 over C total, so I have to take the reciprocal of that number, and you will get 2.1, I think. Yep. And there you go. Okay, and because we were working in microfarads, the answer will come out in microfarads. Okay, now maybe I should just say something about metric prefixes. So a little bit of an aside here for metric prefixes. We have quite a few of them this semester. Okay, so milli you already saw. So like a milliamp or something like that. That's like 10 to the exponent -3. Okay, so if you see here, I'll give you an example, like 1 milliamp, like that, is equal to 0.001 amp, like that. Okay, the next one down is micro. All right, and micro is 10 to the -6, like that. And so if you see like 1 microfarad, like that, that would be 0.12345. They get enough? 1, 2, 3, 4, 5, 6. Yeah, okay. Farads, like that. Okay, and you can see that it gets annoying to put all those zeros there because you have to count the number of zeros and so on. So that's why, micro, like, that's not too bad, but that's pretty hard to read. Okay, and then the next one down is nano. All right, and you will see nano because like capacitors could be very small, so you can see like a nano farad capacitor. That's 10 to the -9, like that. And so like 1 nanofarad, if we got that low, would be 0.1234567 8. farad like that. Let me just make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. Okay. And at this point, it's kind of getting crazy, but there are the small prefixes. Okay. So the ones that are smaller than a unit. All right. So you should know those. I don't know if we had pico in this class, but if we did, that would be 10 to the minus 12. Okay. You can get capacitors down into the picofarads. All right. So great. There's the total capacitance. That's one. What's the total charge? So, we had C is equal to Q divided by V. And I said this is kind of like Ohm's law. And what I meant by that is you can apply it either globally to the entire circuit, or you can apply it locally to one capacitor at a time. Okay. And I said, what's the total charge? So I want, to apply this to the total. Okay. So these are all totals. In other words, the applied to the entire circuit. All right. And what am I asking for? I'm asking for the total charge. That's Q. Okay, so multiply both sides by V total. Q total, that isolates Q total, is going to equal C total multiplied by V total, like that. Okay, and we have those numbers. C total we just found to be 2.1 microfarads, and V total is 10 volts, like that. And the micro, again, just kind of goes along for the ride. I mean, you could just think of it as times 10 to the minus 6. Okay, it's just like it's like another factor in there. Okay, and a farad times a volt, that is a coulomb. All right, and so this is going to equal 2.1. 2.1 times 10 is 21 micro, and then a farad times a volt is a coulomb. All right, so there you go. That is the total charge accumulated on this circuit. Okay, now let's see what I asked next. Good. What is the charge on each capacitor? This is kind of subtle, so students will often make this mistake. That 21 microcoulombs, it's actually the charge not only accumulated by the whole circuit, but it's also the charge accumulated by any individual capacitor in series. And you go, why? How does that work? So let me see if I can try to show you. Maybe I could just redraw this picture down here. Okay, suppose that I accumulate one positive right here on this plate here. Let me put the plates a little bit further apart. Okay, just to make it a little easier to see. Okay, so I accumulate one positive there. Well, that positive there will make a negative over here. Okay, but then that negative over there will make a positive over here, and that'll make a negative over there. Okay, and you can already see what's going on. This capacitor has a charge of 1. I know one side's positive and the other's negative, but it's like positive 1 there and negative 1 there. Okay, so this one has a charge of 1, and guess what? This one also has a charge of 1. Suppose I pushed another positive on here. Okay, so this is a battery. When I say I pushed it, I mean a battery. Well, that positive there is going to push a negative off of there. Now, where's that negative going to go? It's going to go over here, make a positive there. Okay, and then you'll get a negative there like that. Okay, and now you can see that the charge on this capacitor is 2 and the charge on that capacitor is 2. Okay, and you could go on like that. So you could see that whatever charge accumulates on one capacitor, it has to come from the other capacitor. So you get this idea that the charge on capacitors in series is the same on each capacitor. Let's make it clear. Okay, not at all intuitive. Okay, so the charge on each capacitor, let's say it this way, charge on each capacitor in series is the same. Okay, so that 21 microcoulombs, that was the charge on everything, but it's also the charge on one and it's the charge on the other. That's not the case if they were in parallel, okay, but it is the case in series. In parallel, it's pretty obvious, okay, but so that's why I didn't do a problem with parallel. But in series, this is a typical oversight, okay. So not only can I say that the charge on both is 21 microcoulombs, but the charge on this one is 21 microcoulombs, and the charge on that one is 21 microcoulombs. Don't think that you're adding those, okay? Because the charge, that 21 microcoulombs there, came from that plate over there. So it left that plate and accumulated in that plate, and so of course, whatever is the charge on one is the charge on the other, okay? Let me see if there's any questions in the chat. No, okay. Yeah, so a little bit subtle, okay, but now that you understand that, we've answered this question here. Charge on each capacitor. Okay, the charge on each capacitor is in series is the same. So it must be 21 microcoulombs. All right. And then finally, we can ask what is the voltage drop across each capacitor. Okay. Now, you know that the voltage drop across one plus the other has to equal 10. Okay. But you don't know the voltage drop across one and you don't know the voltage drop across the other. And you say, well, how do you do that? Well, back to this formula right here. Okay. So let me take out the subscripts. All right. And again, it's the definition of capacitance, but it's also, it's applicable to the entire circuit globally or locally. Okay. And so I'm asking, what is the voltage drop across each capacitor? In other words, I'm asking for the voltage. Okay. So I could rearrange this formula as, as divide both sides by C, multiply both sides by V. So I'll get that V is equal to Q divided by C like that. Okay, so this is just a rearrangement of that one. I guess I could do it in two steps. So take this and cross multiply by V. So we get CV is equal to Q, and then divide both sides by C, and you'll get that V is equal to Q divided by C like that. Okay, now again, that can be applied globally or locally, but in this case, we want the voltage drop across each resistor. So we want the voltage drop across number 1. Okay, and we could just plug in the numbers. V1 is what we're trying to solve for. Q1 is the charge on C1, and we convinced ourselves that that's 21 microcoulombs. Okay, so the charge on the 3 microfarad is 21, and then divided by C1. C1 was 3 microfarads. There it is. C1 is 3 microfarads there like that. And that's going to equal 7 volts. All right. And look at how nicely the units work out. Okay. You have micro in the numerator and micro in the denominator, so the micros cancel. All right. And then you have a coulomb divided by a farad, and a coulomb divided by a farad is a volt. Okay, so the voltage drop across the 3 microfarad is 7 volts. We could actually write that over here, 7 volts like that. Well, you don't even have to do the other calculation, but this one has to be 3 volts. Why? Well, you're dropping there 7. You have to drop a total of 10. So if you've only dropped 7, you're going to have to drop another 3. Okay, across there like that. All right, so so the next one's got to give you 3, and take this formula, but now you apply it to C2, and that's going to give you not 3. Well, better put the micro back in there. Hold on, don't want to. There we go. We need a micro there and a micro there. Okay, and it's 7 microfarads. Okay, so C2 is 7 microfarads. So we have 21 microcoulombs divided by 7 microfarads. 7 divided by 21 is 3, and it's going to give you volts. Okay, and so as we expected, the voltage drop across the 7 microfarad is going to be 3 volts. Okay, and well, there you go. All right, and no, again, kind of simple, but I think you can see the intuition there. Okay, because the charge on each one of them is the same, the smaller capacitor has to have a bigger potential on it to sustain the same amount of charge. Okay, so remember, because charge, capacitance is how much charge you get per volt. Well, if the charge on both of these has to be the same, then you need the bigger voltage on the smaller capacitor, okay, to get the same charge. Okay, and so on the 3 microfarad you get 7 volts, and on the 7 microfarads you get the 3 volts. Okay, so I hope that that helps you to gain some intuition into how these capacitors work. All right, so I don't want to say, look, this is the simplest you're going to see. You can see circuits with 3. Let me give you an example. Like, you could see a circuit like this on the test. Expect to see a circuit like that. Even though I'm not going to do it right now, you could see a circuit maybe like this. All right, and I don't know, let's put let's give this like 5 kilo ohms, like that. All right. Either with resistors or capacitors, okay. But I don't want to do a problem like that because I did problems like this already, and also it's just more details of the same stuff. What you would do for a problem like this is you would first say, well, which ones are in series and which ones are in parallel? You might think, well, these two are in series and I can condense those, but you can't because there's a junction in between. So what you do is you take a look here and you go, oh, well, the 3 and the 7, they're in parallel, and so you can replace this. You take out the 3 and the 7, okay, take out the 3. Well, actually, let me just do it like this. Take out the 3 kilo ohm and the 7 kilo ohm there, like that, and you replace it with whatever the effective resistance is, like that, okay. And so you know, this circuit here, which had these two in parallel, the two in parallel get condensed into just one, okay. And now you take a look at these and you go, well, these two are in series, and you know how to deal with that. All right. So you know, it's just one extra step in there in terms of condensing your resistors down. All right. So I'm not, like I said, I'm not going to do a problem like that. Let me take a look at in the chat here. Okay. Let's go on because I don't want to make this stream too long. Okay. So great. What else did we do in with capacitors and resistors? Well, another thing we did was we put capacitors and resistors in series. And when you have a capacitor and a resistor in series, what happens is that you can either put some charge on the capacitor and let that charge discharge through the resistor, in which case you get an exponential decay. Or you could say, well, you know what, I'm going to start with no charge on my capacitor, and I'm going to allow my capacitor to charge up off of a battery. But of course, it's gaining that charge through a resistor, and so it doesn't gain the charge immediately. It'll charge up, and so that's an exponential increase, okay? So in this problem here, I did the exponential decrease. I said, look, we're going to take a 50 kilo ohm resistor, and we're going to put it in series with a 50 nanofarad capacitor, okay? And we're going to charge the capacitor to 100 microcoulombs to start with, okay? And then we're going to let the I should probably put another thing here, another sentence in there. We let the capacitor discharge through the resistor. Okay, I think that's implied, but I'll say it, okay? So then there's two questions here that I'm asking. What is the time constant? So the formula that describes this is going to be Q is equal to Q naught exponential minus T divided by, I don't have a tau symbol ready. Let me just write the word tau, okay? Like that, okay? So that's for the, that's for discharging. So whenever you see discharging, you use this one. If it were charging, which is not our situation here, but just so you know what that formula is, it'd be this one minus the exponential, like that, okay? So the first thing to do is say, am I charging or discharging? Well, discharging, well, then we use this formula, not that one, okay? And the time constant is this tau, okay? So tau for a RC circuit is just going to equal R times C. It's very simple. You just take the resistor and you multiply it by the capacitor, and that'll tell you tau. Tau is the characteristic time for how long it takes this to discharge, okay, for the capacitor to discharge. The bigger the capacitor, the longer it takes to discharge, because the capacitor will hold its charge longer, okay? The bigger the resistor, the harder it is to get a current through it so that it discharges, and so the longer it takes to discharge. So bigger R or the bigger C, or bigger both of them, you're going to get a bigger time constant, and the bigger the time constant, the longer it takes to discharge. All right, so the first question is, what's the time constant? Well, it's just R times C, so R is 50 kilo ohms, like that, and C is 50 nanofarads, like that. All right, and so we've got 50 times 50, all right, and 2,500 here. We've got the K, which is 10 to the 3, so I'm going to put times 10 to the 10 to the 3, like that. That's the K. We've got nano, which is times 10 to the negative 6. All right, so the 2,500, that's the 50 times 50. The K here, kilo, is the 1,000, or 10 to the 3. The nano is 10 to the minus, 9, not 6, right here, 10 to the minus 9. Okay, and the ohms times a farad, you go, what is that? Well, I won't go through the units now, but it turns out that an ohm times a farad is just a second. Okay, it's just a time unit. And so what's this going to equal? Tau is going to equal, let me do it on my calculator so I won't make a mistake. Multiplied by 10 to the exponent. It's this number right here. Okay, and that's in seconds. All right, now on a test I'd probably convert that to milliseconds, so that's 1, 2, 3, so that would be 2.5 milliseconds. All right, so there you go, there's the time constant. Now you're going to need that to plug into that formula right there. Okay, so now the next question is, how long does it take until it reaches 20 microcoulombs? So remember, it's starting at 100 microcoulombs. We charge up the capacitor, and the capacitor is discharging. It's kind of like you shorted out the capacitor so that the electrons can travel from one plate to the other. But they can't do it right away because there's a resistor there, and the resistor is resisting the current. So it limits how fast the current can travel through that resistor. Okay, and so that's what the time constant is characteristically. How long does it take for this thing to discharge? And so it's going to start at 100 and it's going to go down to 20. How long will that take? Well, that's where this equation comes into play here. Okay, like that. All right. Now, I mean, I guess I could substitute in the numbers. I would rearrange it first, but I could substitute into numbers. Q is the charge right now. Okay, so the charge is going to come down to 20 microcoulombs. So Q is 20 microcoulombs. Okay, that's got to equal the initial charge. And the initial charge, I said, was 100 microcoulombs. Okay, so whoops. Let me just scroll that down there like that. Okay, sorry, you can't quite see it off of the end there, but it starts off at 100 microcoulombs. All right, so over here, this one's going to be 100 microcoulombs. That's your Q naught. All right, then it's multiplied by the exponential of negative t is what we're trying to solve for, because t is the time. So whenever you see how long, and I'm asking for time, okay, divided by, and tau we can now write in as 2.5 microseconds. Okay, so there we go. There's that formula with all the numbers plugged in. Microcoulombs on one side, microcoulombs on the other side, they'll cancel. Okay, so this becomes just 20 is equal to 100. All right, like that. And 20 divided by 100 is 0.2. Okay, so I'm dividing both sides by 100 and I get that. And this is usually where students get stuck, because they say, well, I'm trying to solve for t. What do I do? Do I divide out the exponential? How do I do that? Well, you have to use the natural log, because the natural log and the exponential undo one another. So if I take the natural log of one side and I take the natural log of the other side, this, and you say, well, that made it worse. Not really, because when you have log and exponential side by side like that, if you take a number, starting from the inside here, you take a number, you exponentiate it, and then you natural log it, what happens? You get the number back again. So this whole thing here just becomes the log and the exponential. It's kind of like they cancel one another out like that, and you just get this. Okay? And now what? Well, we can calculate the natural log of 0.2. It's a negative number. Let me see what it is. It's this number right here. Okay, and that's going to equal negative t times 2.5. All right. Now there's a negative on both sides, so we can cancel out the negatives on both sides. All right, and then we've got this number here. We can multiply it by 2.5 milliseconds on that side like that, and that'll give us t. And that tells us that t is equal to, see, multiply by 2.5. That's equal to this number right here. Okay, and that's going to be in microseconds. All right. So, in this circuit, now, sorry, I said milliseconds. Okay. Millisecond is 1,000th of a second. That's too fast for us to see this happening, but this would be very easy to measure on an oscilloscope. Okay. So, you'd set your oscilloscope to trigger when it, well, you trigger oscilloscopes off of voltages, but the equivalent of when the capacitor has a 20 microcoulomb charge on it, and it'll trigger, and then you'd be able to see the exponential decay on that. And you say, well, how long did it take to get from that 100 microcoulombs down to 20? You probably throw a switch, and that's when the discharging begins. And the answer the oscilloscope will give you is that it takes just a little bit over 4 milliseconds for the charge to drop from 100 to 20 microcoulombs. Okay, so there we go. We've got a problem here, which is this is basically a let's see here, an RC circuit. Okay, so that's what that problem is. All right, now the next problem I'm going to do, I better check the chat here. Okay, there are no questions so far. The next problem I'm going to do is a little bit out of order. Okay, and that's okay. The reason I'm doing it out of order is is because I want to compare the RC circuit to an RL circuit. Okay, and C, of course, stands for capacitor, whereas L stands for an inductor. And inductors are a bit confusing. Okay, people tend to understand what a capacitor does. It just stores charge. Okay, but what does an inductor do? Like, what's its purpose? I mean, you can make it out of a solenoid. We'll see that in a minute when we do magnetism. But what does it do in a circuit? What it basically does is that once you get a current going through an inductor, it doesn't matter how big or how small that current is. The inductor does not like a change in the current. Okay, so if you have like a 1 amp current going through an inductor, the inductor says, great, no problem, we can continue with this current. But if you try to drop that current very quickly, the inductor goes, no, you're not going to drop this quickly. You're going to have to drop this slowly. It kind of limits the rate at which currents can change. If there's no inductance in a wire, there'd be no reason why you can't go from like 1 amp to 0 amps right away. Okay, so no inductance, you're at 1 amp, you throw a switch and it drops down to 0 amps right away. No inductance. But if there's an inductance, you turn off the current, the inductor goes, nope, you're going to have to slowly go down to 0. Okay, from 1 amp you slowly go down to 0. The bigger the inductor, the longer it takes for the current to wind down to 0. So you can think of this inductor as just kind of like always pushing the current. Okay, it just says, no, I don't want you to slow down. I'm going to keep pushing you. And the energy that it gets to keep pushing that current comes from a magnetic field inside the solenoid. Okay, so, or inside the inductor. I said solenoid because usually you make an inductor out of a solenoid, but there are other things that can be used to make inductors. All right, so if you put an RL circuit together, you get a similar decay. If there's no resistance and you just have an inductor and it's in a circuit, and you put a current in there, say 1 amp, what does the inductor want to do? It wants to keep the 1 amp. And so that current, that 1 amp current is just going to go forever and ever and ever and ever and ever and ever. Okay, it's never going to slow down from 1 amp. And the reason is because there's no resistor. If you put a resistor in there, and the resistor is going to dissipate away some of the heat, it's going to slow down the current, and eventually, yeah, it'll go from like 1 amp down to 0 amps. Okay, the bigger the resistor, the faster it drops. The bigger the inductor, the slower it drops. Okay, so the time constant is a little bit different, and for an inductor or for an RL circuit. Okay, so let's read this problem. You'll see that the numbers are kind of similar to the previous problem because I want to show you that the two are quite similar. Okay, so now we have a 50 kilo ohm resistor, same as above, and a 50 microhenry inductor in series. Okay, the units for inductance are henries. Okay, and typical inductors are in the millihenry range. Okay, so a 50 kilo ohm resistor and a 50 millihenry inductor. Okay, and I'm going to start it off with an initial current of 100 milliamps. Okay, so what is the time constant and how long does it take for the current to drop to 20 milliamps? I think you could see the similarity. Before I was not talking about currents, I was talking about charges. So I start with 100 microcoulomb charge and I drop to a 20 microcoulomb charge. Here, I'm going to start with 100 milliamp current, and I'm going to drop to a 20 milliamp current. Okay, and I want to know how long. All right, so the formula here looks an awful like this one, except that when we're talking inductors, we're not talking charges, stored charges. We're talking currents. And so the current at any given time is equal to the initial current, I naught, multiplied by the exponential decay factor. Okay? And tau, in this case, I mean, it's not RC because we don't have a C here. It is L divided by R, like that. Okay? That is the time constant for an LC circuit. The bigger the inductor, the longer it's going to take. Okay? And the bigger the resistor, the faster it'll stop the current, because resistors really want to resist current. They want to stop it. So in this case, the resistance is in the denominator. Okay, so the first question is, what is the time constant of the circuit? And it's just this formula right here. And that's going to equal, L is 50 millihenries, like that, divided by 50 kiloohms, like that. All right, and that's going to give us tau is, well, the 50 divided by 50, that gives you just 1. All right. The milli is 10 to the, we better be careful about this because we might make a mistake. The milli is 10 to the minus 3 divided by the kilo, which is 10 to the 3. Okay, so we have a 10 to the minus 3 in the numerator and a 10 to the 3 in the denominator. And then the final units, we don't need that leading one there. Okay, so that's just the numeric part. Okay, the units are going to be a Henry divided by an ohm, like that. And you say, what unit is that? It's time. It's seconds. Okay, so this is actually going to equal 10 to the minus 3 divided by 10 to the 3 is 10 to the minus 6. And a Henry divided by an ohm is a second. So that's 10 to the minus 6. And 10 to the minus 6 is micro, right up here. Okay, so it's going to have a time constant of a microsecond, which is pretty fast. Okay, a millionth of a second. Whoops, I better put the 1 back in there. Okay, so there's my time constant, 1 microsecond. All right, check the chat here. All right, great. Now what? Well, how long before the current drops down to 20 milliamps? The math is almost identical to the previous one. Okay, so you start with this formula there. The initial current, sorry, the I is the current. The current right now. Okay, and that's 20 milliamps. I naught is the initial current, and that was 100 milliamps, like that. And now we have the exponential of minus t divided by tau is 1 microsecond. Okay, and so 20 divided by 100 is 0.2 on the left-hand side, and then we get this exponential there like that. Take the natural log of both sides, just like we did above. That's going to equal minus t divided by 1 microsecond. Like that. The natural log of 0.2 is we just had this number, but there it is. And that's going to equal t divided by 1 microsecond. Multiplied by both sides by 1 microsecond, and you're going to get that. It's going to equal 1. Well, we should round off to 3 significant figures. So there it is. It's going to be 1.61 microseconds. Okay? So there we go. That answers this question here. So I know this is not the order in which I presented the material, but I wanted to put the RL circuit and the RC circuit side by side so that you could see how similar they are. You don't have to really memorize a lot more stuff. The only thing that you have to recognize as being different is, well, with the inductor, of course, the time constant is calculated differently. And also with the inductor, you're talking about changes in current over time rather than changes in charge over time. Okay, you can talk, with the RC circuit, you can talk about, currents in that circuit, but we tend to talk in terms of the charge on the capacitor. Okay, so there you go. All right. Let me see if there's any questions in the chat. All right. Nope, none so far. All right. So now we're getting into magnetism. State the right-hand rule for a wire. I guess I should have said a wire carrying a current, a solenoid, and the Lorenz force. Okay, so the right-hand rule shows up over and over and over in magnetism because magnetism is a chiral force. And what a chiral force means, it means that it's like there's a difference between left and right-handedness. Okay, that's not the case with electricity, and it's not the case with other like Newton's laws and things like that. But it is the case for magnetism. In other words, magnetism knows the difference between right and left-handedness. Okay, and that's why this right-hand rule comes up all the time. All right. So what is the right-hand rule for a wire? Well, it's basically part of Ampere's law. And Ampere's law says if there's a wire carrying a current, then it creates a magnetic field. Okay, so a current. Ampere's law says a current creates a magnetic field. But what direction is that magnetic field in? In other words, if you put a compass there, which way would it point north? And the answer is, so this is the right-hand rule for a wire carrying a current. You point your thumb of the right hand, in the direction that the positive current is traveling. Positive current means, imagine that the current is traveling from the plus side of the battery to the negative side of the battery. Okay, that's just a convention. Okay, I mean, what's happening at the microscopic level? Are the electrons moving? Are the positive things moving? Don't worry about it. Just, point your thumb in the direction of the positive current, that is from the positive to the negative. Okay, and your fingers will automatically curl around your thumb. See how, here, I'll point it this way. See how my fingers are curling around my thumb and they're kind of pointing that way? Fingers are pointing that way, like that. Okay, the fingers of the right hand will then point in the direction of the magnetic field. This is basically showing a circulation around the wire. The magnetic field is not parallel to the wire. It actually circulates around the wire, and it circulates around the wire this way because that's the way in which my fingers point. Okay, so that's the right-hand rule for a wire. Point the thumb of the right hand in the direction of the positive current, and the fingers will point in the direction of the magnetic field. In other words, they'll point north. Okay. Just to be very clear. Now for a solenoid, it's the other way around. You point your fingers in the direction of the current and your thumb will point in the direction of north. Okay? You can actually use, I don't want to confuse you, but you could actually use the wire one for the solenoid. You can use the solenoid for the wire. And they're consistent with one another, not like they're in contradiction. But it's just easier that, if you say wire, point the thumb in the direction of the current. For a solenoid, point the fingers in the direction of the current. Okay? And now for the Lorenz force, this one is even more different. Yeah, maybe I should, well, we're going to do a Lorenz force calculation in just a minute. But for the Lorenz force, you have, I better write it down. I better write down what the Lorenz force formula is. F is equal to QVB sine theta, like that. Okay. That's for a single wire. That's for a single particle, not a wire. But there's the equivalent one for the wire. But basically, what the Lorenz force says is that if there's a charged particle and it's traveling through a magnetic field, then there's a force on that charged particle. But it's a funny kind of force because it actually depends on how fast that charged particle is moving. So, if you've got a charged particle and it's just sitting there not moving in a magnetic field, the magnetic field everywhere, but this charged particle is not moving. It doesn't know it's in a magnetic field. It doesn't feel any force at all. As soon as the charged particle starts to move through the magnetic field, it goes, oh, there's a force on me. Okay, and the way this one works is you have a velocity vector, v, and you have a field vector, b. Okay, direction of the magnetic field lines. Remember, the magnetic field lines point towards north. Okay, so you put a compass there, the compass will point north along with the field line. All right, so how does this one work? Well, first of all, if V and B are parallel, there's no force because then theta would be 0. So V and B are not parallel to one another. They're at some angle to one another. It could be anything. It could be 90 degrees, it could be 10 degrees, whatever. Okay. Now, what you have to imagine is you imagine that these two vectors are like the hands of a clock. Okay, so maybe let's see, I'll use my finger for B field and I'll use my thumb for velocity. Okay, and so the velocity is this way and the B field is this way. You rotate the velocity towards the B field. So just imagine that rotation. You go, what direction am I rotating in? You're rotating this way. You're rotating this way. See how my fingers point now in the direction of that rotation? Your thumb will point in the direction of the force. Okay? So I'm going to write this one down because it's the hardest of the three, obviously. So this is for the Lorenz for the right hand rule for Lorenz force. Point fingers of right hand in the direction of the rotation of the v vector to the b vector, and the thumb points in the direction of the force. Okay, well, almost. Okay, that's what I've said so far. So we've got V one way and we have the magnetic field the other way, and we're rotating B to V and point the fingers in the direction of the rotation, and the thumb is going to point the force in this case towards me. Okay, and for a positive charge, that's the other part. Okay, so we'll add that for a positive charge, and in the opposite direction for a negative charge. So after you've done all your magic with your hands and you've decided, oh, the force is this way, say towards me, then you're going to say, oh, but it's a negative charge, so it's the other way around. Okay, so that's the right hand rule applied to the Lorenz force. There are other ways of formulating it online. I could have given you all of them, except that it would probably have overwhelmed you. Okay, so if you look up, right hand rule for Lorenz force, you might see different formulations of it. Some people will do it in terms of three vectors. They make three vectors with their fingers like that. But let's just stick with this, okay? And on the test, because they're multiple choice, I would just ask you these things verbally anyhow. I guess I could give you diagrams, but I didn't. So, okay, so there's a little bit of a hint. Okay, great. There's the three right hand rules. Okay, and see if there's any questions on that. All right. So now what? Okay. So what is the force on a What is the force on a 1 gram water droplet carrying a 15 microcoulomb charge? Let me put that in there. Carrying a 50 microcoulomb charge. If it enters a 2.5 Tesla field, such that the velocity vector and the B field make a 55-degree angle. Okay, and okay, so that's question A. And then I also ask for what is the cyclotron accelerate? What is the acceleration? What is the cyclotron radius? And what's the cyclotron frequency? Okay, so let's do that. All right. So the first thing is, what is the force? And so you've got a charged particle. This droplet of water has some charge on it, and it's entering a B field. And you say, well, there's the Lorenz force on it, and there's the formula. Okay. Now maybe I should just contrast this with the other one. The other one is like if it's a wire carrying a charge, then it would be F is equal to IL B sine theta, like that. Okay, where I is the current, L is the length of the wire that's in the magnetic field, and the rest is the same. Okay, these two are actually totally equivalent to one another, and I showed that during the one lecture. You can take one and morph it into the other one and vice versa. Okay, but in the middle of a test, you're going to go, well, which one do I want? Well, are you talking about a wire carrying a current? If yes, then you use this one. Are you talking about, some little droplet, some particle, something like that carrying a charge and moving? Well, yes, then you use this one here. Okay. Well, in our case, we have, a droplet, which is not exactly a particle, but it's close enough. Okay. And so let's calculate this. So we have F is equal to Q. Q is the charge. And I said the charge was, a little clip there. Here, let me do this. There you go. You should be able to see that now. Okay, so I told you that it's got a 15 microcoulomb charge. So let's just put that in here. The velocity, I tell you, is... Oh, I didn't tell you the velocity, but I'm going to tell you now. assume the droplet is traveling at, I don't know, 15 centimeters per second. Okay, that's pretty fast, but it's all right. Okay. All right, so the velocity, I just said it was 15 centimeters per second, but that's not MKS. We'll convert it in a minute. Okay, and the B field I said was 2.5 Teslas. All right. Now that would be the force if the velocity and the B field were like perpendicular, 90 degrees to one another. That's when you get the most out of the Lorenz force. If they're parallel, there's no force at all. Okay, so V and B are in the same direction. You're not going to get any force at all. You fire a charged particle into a magnetic field and it's traveling along the field lines. It doesn't know it's in a magnetic field. It's only when it crosses across these field lines. Okay, and so that's where this sine theta comes in. And I tell you that the angle is 55 degrees. Okay, so almost ready, except that we got to put everything in MKS. Micro is 10 to the minus 6, so we've got 5 times 10 to the negative 6 here, like that. Whoops. And we got to convert this to meters per second. Centimeter, divide by 100 to get meters, so that's 0.15 meters per second. And then 2.5 Teslas, that's already in MKS, and then we got to do sine of 55 degrees, like that. Okay, and I should be able to cut and paste this directly into my calculator. Oh, it doesn't like something. Oh, I know what it doesn't like. It doesn't like the sine. Oh, there's something else it doesn't like. I don't know. What's it not liking? Multiplied by sine of 55 degrees. Ah, there we go. All right. So it's got this number here, which has a lot of zeros in front, but I kind of expected that. Okay, that's going to come out in newtons. All right, and now let's move the decimal over. 1, 2, 3, 4, 5, 6. Okay, so that's going to be 4.61. Let's do that again. So here's the decimal. 1, 2, 3, 4, 5, 6. 4.61 micro newtons. Okay, like that. All right, so very, very small force. Okay, on this charged particle. All right, so did we answer the question? What is the force? Yes. Okay, what is the force on a 1 gram droplet of water carrying 15 microcoulomb charge if it enters a 2.5 Tesla field such that the velocity and B vector make a 55-degree angle? Assume the droplet is traveling at 15 meters per second. Okay, so great. There's the force. All right, now that's part A. Part B is what's the acceleration? And F is equal to ma. All right, so we want that acceleration due to that force. That's just going to be F divided by m. So here is there's the force divided by the mass is 1 gram, but we have to convert that to kilograms. So as a kilogram, it's 0.001, like that, kilograms. Okay, and now if we work that out, we're going to get 4610. Oops. A is going to equal. So it's like moving the decimal over. See, 1, 2, 3 here. It's like moving the decimal over 3. 1, 2, and then 3. Okay, and we still have that micro there. And this is going to be a newton divided by a kilogram, meter per second squared. Okay, so I hope I didn't go too fast there, but basically this is saying 4,610 micrometers per second squared is the acceleration. Or if we move the decimal over 3, 1, 2, 3, micro becomes milli. So 4.61 millimeters per second squared. Okay, so there's your acceleration. All right, very, very small acceleration. Okay, compared, like gravity would be, gravity is like 9.8 meters per second squared. Okay, this is 4.61 millimeters per second squared, so it's very tiny. All right, great. Let's go on. what would be the cyclotron radius? And so at this point, you kind of got to remember some of the uniform circular motion that we did last time. Now, technically speaking, this, because it's not at 90 degrees, it's not going to do uniform circular motion. It's actually going to make a spiral. Okay, because there's part of the velocity component which is perpendicular, and that's the part that gives you the uniform circular motion. Then there's a part that's moving. Okay, so you got to just be careful about that. But you could still, even if it's spiraling, you could still talk about a cyclotron radius. Okay, because if it's spiraling, you know, like let me do a spiral towards you. You could see that, yeah, my finger's getting closer, but the spiral has a kind of a circular shape to it, and there's a radius to that shape. Okay, what is the radius to the of the spiral? Okay, and that's also known as the cyclotron radius. Okay, so you don't have to worry that it's actually a spiral. You could just, you know, make use of the numbers that we have so far, and we want the radius. And you say, well, is there a relationship between the radius, the acceleration, and the velocity of an object in uniform circular motion? And yeah, there is. Okay, A is equal to V squared divided by R. Okay, so the centripetal acceleration is equal to the velocity squared divided by the radius of the uniform circular motion. Well, we have A, we have V, and we want to calculate R, and so R is going to equal V squared divided by A. Okay, now you know what, let me get rid of this. We better be careful here. We better be careful because let's convert this to actually to MKS so that we don't confuse ourselves. So 461, like that, meters per second squared. Okay, let's make sure we did that right. So originally it was this number here. Let's put a little 0 there. Okay, see if I did this right. So that's 10 to the minus 6. So if we want to convert this to just meters, from micrometers to meters, we have to move the decimal over to the left 6. So here's where the decimal was originally, right after the 0, on the right hand side of the 0. So that's 1, 2, 3, 4, 5, and 6. Okay, see, I did it correctly. Okay, so there's the acceleration expressed as meters per second squared. Okay, that's what's going to go there. The velocity, I said, was 15 meters per second, but again, we got to do that in meters per second. So we're going to have 0.5 meters per second for the velocity, all squared, divided by this acceleration here, like that. Okay, and that's going to give me a radius of, tell you in a second, 0.15 squared divided by 0.00461, and it's equal to this. Okay, 4.88. Since everything here was in MKS, that is in meters. Okay, so yeah, it's a tiny acceleration, but it's enough that you're going to get a circle with a roughly 5-meter radius. Okay, or, you know, imagine a circle which is like 30 feet in diameter is roughly how big this is going to be. Okay, so yeah, you know, you're going to get this kind of circular motion happening with when this charged particle enters the magnetic field. Okay, and then the last question was, what would the cyclotron frequency be? And here there's a few ways to do this. The one I like using is V is equal to 2 pi R divided by T. Okay, now remember, T is the period, but you can relate the period and the frequency as T is F is equal to 1 divided by T. And so I could just rewrite this as, instead of divided by T, just multiply by F, like that. Now, we want to solve for F. What would the cyclotron frequency be? So we have F is equal to V, and then divide both sides by 2 pi R, like that. And that should give you the frequency. Okay, now do we have all those numbers? Yep. Okay, the velocity is 0.15 meters per second divided by 2 times 3.14 times the radius, which we found to be 4.88, and this is going to equal, give it to you in a second, a really, really small frequency. Okay. Yeah, it's almost silly to write it as this frequency because um, it makes only a fraction of a turn every second. Okay, it makes like point like half a percent turn of a turn every second. So it might make more sense to do this in terms of the period. Let me do that. I know I didn't ask it that way, but I just made up these numbers. I didn't actually solve them beforehand, but this would be the period. Okay, in seconds. Okay, and if I divide that by 60, I can give it to you as how many minutes? Like 3.4 minutes. Okay, so um, this droplet would go in a circle. Where did we find the cyclotron radius? Right here. It would go in a circle, which is just a little short of 5 meters radius. Okay, and that's like 15 feet radius or 30 feet diameter. Okay, which is a big circle. Okay, and it would take about 3.4 minutes to go all the way around or make that cycle once. Okay, so there you go. There's the cyclotron radius and cyclotron frequency for this charged droplet. All right, see if there's any questions in the chat here. Let me get a drink. I've done these long streams before. I've done streams up to 3.5 hours long, and I've learned to have some actually have Gatorade ready because otherwise your voice goes after that much time. But okay, well let's push forward. All right, so there's that question. Okay, so what's the next one? Well, the next one is about flux, magnetic flux. So the way an electric motor or sorry, an electric generator works is you'd have like something like a loop of wire, and you have magnetic field lines through that loop of wire. Okay, and that loop of wire is sort of like containing so much magnetic field lines. That measure of how much magnetic field lines it's containing is called the magnetic flux. Okay, in itself it's not that interesting. It's when the magnetic flux changes, and it could change because the loop turns, it could change because I shut off the magnetic field or turn up the magnetic field, or the orientation of the loop turns. Okay, whatever. I could squish the loop down and increase it. Any one of those parameters change, and what you're going to find is that you induce a current. Okay, and so first we're going to calculate the magnetic flux. Okay, so let's see how we do that. So part A says, what is the flux on the Earth's magnetic field? What is the flux of the Earth's magnetic field through a circular loop with a radius of 1 meter? Okay, and assume that the loop is at 90 degrees. So say the magnetic field lines are running parallel like this to the ground, and you just got this big loop here, like a 1 meter radius loop of wire, and you're saying how much flux is contained inside that loop of wire. Okay, and flux is calculated as follows. It's given the symbol phi. I don't have a symbol phi ready to hand, but it's it's the one that's done like that. Okay, like the Greek letter phi. You'll see it in the notes, and that's going to equal B times A times the sine of theta. Okay, where B is the strength of the magnetic field, A is the area that the wire encloses, the loop encloses, and theta is the angle that the plane of the loop makes with the magnetic field. Okay, so I wrote something funny here. I don't know why I put that and 0 theta there like that. Where the plane of the loop is 90 degrees to the field. Okay, that's good. Okay. All right. All right. So phi is going to equal the strength of the magnetic field. So the Earth's magnetic field, it varies a lot, but we'll say it's 75 milliteslas. And I guess I should have calculated the area of the loop first. That's easy enough to do. The area of the loop, it's a circular loop. It's going to be pi r squared. Okay, and so pi is 3.14. And r, I made r really easy. I made it 1 meter like that squared. And so the area is going to be 3.14 meters squared like that. Okay, so for B, we have 75 milliteslas. For A, we have 3.14 meters squared like that. And then sine, and the angle, I said the loop's plane makes a 90-degree angle to the field. Okay, and so that's what theta is. That's that angle there, and so this is going to be 90 degrees. Sine of 90 degrees is 1. Okay, so this part here gives you 1. All right, what's the rest of it give you? 75, whoops, 75 multiplied by 3.14 is going to be 235.5, but it is not just Teslas, it's micro Teslas and meters squared. Okay, and sometimes I put a little dot in there, it helps to read it a little bit better. I don't know, that looks a little funny to me, but there we go. Okay, now normally the units for flux are Tesla meters squared, like that. Okay, which is kind of a strange looking unit, but you know, if you want to put a prefix in front here, you can. So this is going to be microteslas per meter squared. Okay, like that. All right, so it's pretty small. All right, great. So not that interesting in and of itself. You're just saying, look, that's how much field lines is being captured by the loop. The next part is where it gets interesting. Okay, so let's read that. What voltage is generated if the loop turns from 90 degrees, those field lines are like this, turns from the 90, so my hand is like the plane of the loop. So the plane of the loop is this way and the field lines are this way perpendicular. I'm going to just turn the loop from this to this. Okay, so that it's at 0 degrees. So when it's 0 degrees, so let's say first at 90 degrees, you have a flux of this. All right. But at 0 degrees, well, what's the sine of 0? Okay, sine of 0 is 0. At 0 degrees, the flux is 0. Like that. Okay, Tesla meters squared. All right, so, you know, you're going from this certain value of the flux to 0. And you're doing that, and I said, okay, so let's read the whole question. What voltage is generated if the loop turns from the 90-degree position to the 0-degree position in 150 microseconds? Okay, so that's when electricity is generated, and that's how an electric generator works, by changing the flux one way or the other. Either you change the rotation, change the orientation of the loop, which is usually how it's done. Okay, because you know, it's kind of hard to do the other ones, or you could change the flux. So it's a magnetic field. Okay, you can like turn on or turn off the magnetic field. That's kind of hard to do if you're using bar magnets as part of your generator. And the other one is you could actually like deform the loop, changing the area. But it makes sense to just like kind of rotate the loop. All right. So what voltage is generated if the loop turns from the 90-degree position to the 0-degree position in 150 microseconds? And that is this formula here. The voltage generated is going to equal delta, the change in the flux, divided by the time. Okay, so you know, the bigger the change in the flux, the more voltage you get. The quicker the change, the smaller the delta t is, the more voltage is generated. Okay, well, the delta phi is easy because it's just that number there minus 0. Okay, in other words, it's that number there back again. Okay, so there's your delta phi. You're going from 235 microtesla meters squared down to 0. Okay, divided by, and the time it takes to do that is going to be the 150 microseconds, like that. All right, and the micros cancel out very nicely. Do that actually on another line like that. Okay. And you might wonder, what is a Tesla meter squared per second? And it turns out to be a volt. And so the voltage you're going to get here is going to be 235.5 divided by 150. 1.57 volts. Okay. So that's kind of interesting. Let's just think about what I just did here. If I have this big loop, okay, so it's remember, radius of 1 meter, and I rotate it very quickly. That's the hard part of this, because you got to rotate it in 150 microseconds. But if you could, you would actually generate a little over 1.5 volts of electricity in that wire, just from the Earth's magnetic field. Okay, so I don't know if anyone's ever tried to engineer an electric generator that way. Usually these generators come with big magnets already built into them, but that might be interesting, to just try to generate it directly off the Earth's magnetic field. Okay, so there you go. There's an example of a magnetic flux problem. Okay, see here. All right, so still got 6 people watching the stream. All right. Okay, 2 more questions for the non-calc stuff, all right? And the first one is, what is the inductance of a solenoid made up of 1,500 windings of wire with cross-sectional area 12 centimeters squared and length 7.5 centimeters? Assume no core. I might do a part B, and I'll show you what to do if you have a core. So we now saw what an inductor is. It's this device which tries to resist changes in current in a circuit. Okay, how would you build one? Well, it's basically built out of a solenoid, and what the solenoid does is, because it's got these multiple loops of wire, it does this thing called self-inductance. Okay, if you have a loop of wire, and if the current changes in that loop of wire, then the amount of magnetic field in that generated by that loop of wire decreases. Okay, that makes sense. Okay, but then when the magnetic field decreases, it's going to induce a magnetic field in another loop of wire, and that because of Lenz's law, is going to try to induce a magnetic field in this other loop of wire in the opposite direction to resist the change. And so every time the current changes, there's a self-inductance which tries to resist that change, okay, through an induced magnetic field in another part of the solenoid. And so the solenoid is interacting with itself all along the length of the solenoid, where reducing current in one is inducing a magnetic field in another to try to increase the current. So current goes down in one part, and another part says, no, I want the current to go back up. And vice versa, everywhere along the solenoid. And so the solenoid is basically saying, nah, I really don't want to change my current. It's acting like an inductor. Okay, what's the formula for this? So the formula for this is the symbol for inductance is L, is equal to mu naught, which is the permeability of free space. Okay, permeability of free space, multiplied by n squared times A, divided by, let me get rid of the brackets here, divided by L. Okay, and let me explain all the pieces. Mu naught is the permeability of free space. It's the ability of free space to sustain a magnetic field. Given a certain amount of current in a certain area of free space, empty space, how much magnetic field is created. That's what mu naught is. Okay. Now, if there's something there, some material, then there's an enhanced enhanced permeability, and that's what this no core means. It means you're just going to use the raw mu naught there. Okay, raw value mu naught. N is the number of windings, but notice that the inductance goes as n squared, and the reason is that every coil, every loop, is going to interact with every other loop. And so n loops are going to interact with n other loops. That leads to a factor of n squared, okay, which is kind of interesting. You wouldn't expect that, but there it is. A is the area, and why is the area showing up there? Because this is a flux phenomenon. It's the flux inside of that, inside of the solenoid. And the flux, you just saw a minute ago, is calculated by not only the magnetic field, but also the area. So the solenoid is creating a magnetic field, but it's creating a magnetic field over an area A, which then sees itself, and that's why it's called self-inductance. Okay, so and then L, of course, is the length. Okay, so what is the inductance? So I just made this one a very simple one where you just plug in, you don't have to rearrange. But I could, on the test, I could say, look, the inductance is this, and then ask you to calculate one of the other parameters in there. Okay, so we want to design a solenoid that gives us an inductance of like 50 millihenries. Okay, and then what are the parameters that we need? Okay, this is the formula you use. All right, so mu naught is 1.26 times 10 to the negative 6, okay, in MKS units. N is the number of windings. It's 1500, okay, and that is squared, so we're going to have to square that number. A is the area, and the area has to be a meter squared, and so we got to be very careful here. The area here, I gave it to you in centimeters squared, okay? And you say, how do you convert from centimeters squared to meters squared? A typical error that's made is that you'll just move the decimal over 2, like this, and say, oh, because there's 100 centimeters in a meter, except that that's wrong. That would be correct if it were just centimeters and meters, but you have centimeters squared and you have meters squared. So you actually have to move the decimal over 2. You have to divide by 100 for both centimeters. So it's actually like dividing by 100 and then dividing by 100 again, or by like dividing by 10,000. Okay, so if you've got this here like that, okay, the decimal was originally there on the right hand side of the 2, and you move it over 1, 2, 3, 4. Okay, there you go. All right, or just divide by 10,000. Okay, so it's like 12 divided by 10,000, or 12 divided by 100 and then divided by 100 again. Okay, because there are 2 centimeters that you have to convert, and for each centimeter that you're converting, you have to divide by 100. Okay, so there is our area, and divided by the length. And the length of the solenoid is 7.5 centimeters, but we're going to convert that to, we don't need the meters squared there. Okay, I'm going to convert that to 0.075. Okay, so now we have that in meters. All right, so there we go. There's your permeability of free space. There's the number of windings squared. Okay, there's the area in MKS units divided by the length. Okay, so L is going to equal, let me do this on my calculator. And I get this. Okay, now that's coming out in MKS units, so that's henries. And I would move the decimal over 3 to the right to give you millihenries. So 1, 2, 3. So we get 45.3 millihenries like that. Okay, so there's your answer. All right. Now, for this one, I said assume there's no core. What happens if there is a core? So if there is a core, I have to give you the mu r, then you'll use this equation here, and I would have to give you mu r, which is the relative permeability. So there's an extra factor in front, and this extra factor is mu r, like that. Okay, so where mu r is the relative permeability. It's usually a number like, anywhere, it's got to be bigger than 1 for sure. Okay, but it could be anywhere from 1 to maybe up to 10,000 or something like that, depending on the material. The more the material can sustain a magnetic field, the more it will enhance the magnetic field inside of the solenoid. And the bigger the magnetic field, the more flux there is, and so the more self-inductance and so on. Okay, so there you go. I'm not going to do this, but if I said to you something like mu r is 1,000, well, then this number would be 1,000 times bigger. Okay, because that's the enhancement factor. All right, let me see if there's any questions on how to build an inductor. If you remember from the test number 2, when we talked about capacitors, I actually showed you how to build a capacitor, okay? And this is how you build an inductor using the solenoid. All right, last non-calc question, okay? And most people find optics pretty easy. If you need me to do more optics problems, I will, but they are pretty easy problems. There's just 2 equations you have to worry about. One is the lens maker's formula, which is this one. Okay, so when you do a ray diagram, you've got an object and it is a certain distance from a lens, from a concave or convex lens, and that distance is called DO. That's the distance of the object to the lens. On a problem, I'm either going to ask you to solve for that, or I'd have to give you that number. Okay, then the image is formed. An image is formed somewhere, and that image is a certain distance from the lens, and that distance is called DI, distance of the image from the lens. And then the optical device itself has a focal length F. Okay, and that focal length, well, as a focal point, that focal point is a certain distance from the lens, and that's f. Okay, and the focal point is the point at which all rays that pass through this lens that come from infinity, in other words, rays come in parallel, they will pass through the lens and they'll all go through that focal point. Okay, and so this formula actually comes out of that. I didn't derive it for you, but it comes from just an analysis of similar triangles in the ray diagram. Okay, if there's anything tricky about this at all, it's that F is positive, so F is positive for convex lenses, and F is negative for concave. That's one tricky thing about that equation. And the other tricky thing about that equation is that DO is always positive just by convention, but DI is positive if image is real and opposite side of lens, okay, compared to the object. And the other possibility is DI is negative, and in that case the image is virtual and same side of the lens as the object. Okay, so I don't know if it's tricky or not, but it's just like, just keep that in mind. So some of these numbers in here when you plug in might have to be negative. Okay, let's solve this problem. All right. Oh, there's also the magnification formula, and that's this one. The magnification is equal to negative DI divided by DO. Okay, and that's also equal to HI divided by HO. Maybe I should write it the other way around. The magnification is by definition. When you say how much bigger is the image than the object, it's the height of the image divided by the height of the object. Okay, so that's by definition what the magnification is. By an analysis of the similar triangles, that's going to equal minus DI divided by DO. Okay, so that's what's going on with that formula there. All right. Okay, so let's solve now. An object is placed 15 centimeters from a convex lens of focal length 3.5 centimeters. Okay, so if we do that, what information have I given you? Okay, so the object is placed a certain distance from the lens. That's immediately DO. Okay, and it's 15 centimeters. All right, so that's equal to 15 centimeters. And DO is always positive, just by convention. Okay, from a convex lens of focal length 3.5 centimeters. All right, so that means that your focal length here is F is equal to positive 3.5. I don't have to put the positive in there, but I just want to emphasize that it's positive 3.5. Why? Because this is a convex lens. Convex is the lenses which are thicker in the middle and thin at the ends, or also known as magnifying glasses. Okay, so there's F, and then I asked the question, where is the image formed? Okay, so I'm asking for DI, so we use this formula right here. All right, you get 1 divided by 3.5, we'll work in centimeters, is equal to 1 divided by 15 plus 1 divided by DI. So 1 divided by DI is going to equal 3.5 minus it's going to equal this number here like that. And then to get DI, you take the reciprocal and you will get this number here. Actually turns out to be a 7 if I round up. And we were working in centimeters, so that number is centimeters. Okay. By the way, if you go through the signs very carefully, that turns out to be positive. And so what situation are we in? Well, what's my next question? Well, magnification, but let's take a look at question number C. What type of image is formed? And how is the image oriented with respect to the object's orientation? Okay, in other words, is it inverted or not? Well, let's do this one. What kind of image is formed? Well, if DI is positive, the image is real. Okay, so a real image is formed. Now, if you say, what's a real image? Like, isn't a virtual image real? I mean, it depends what you mean by real, but in this context, real means that the rays will converge to form the image, and the only way you could see them is you can't put your eye there. You have to put a screen there, and the rays will converge onto the screen, and they'll project the image onto the screen. Okay, so because DI came out to be positive, I can conclude that this is a real image that is being formed. Okay, now let's go back to the magnification. So what is the magnification? And that's given by this formula right here. Okay, now if you look at the information I gave you, I said nothing about HO and HI. That's right. You don't need HO and HI to get the magnification. You just do negative DI divided by DO. So that's going to be negative. And DI, we've just said was 4.57. And DO is 15 centimeters, like that. Okay. And that's going to give me a number. What number will it give me? All right. Okay, there it is. So the image is actually there it is, negative, slightly smaller. Okay, so now what? So the image size is 0.3. It's like 30% the size of the object. Okay, and the negative means that it's inverted. Okay, so the image is actually inverted. All right, so that answers this part. How is the image oriented with respect to the object? So the object is upright and the image is inverted. Okay, so that ends the common part of the entire stream. Okay, that is common to both the calculus and the non-calculus students. Let's for the 112, let's call it a quits right now. And for the 102, let me go ahead and show you some of the stuff on the calculus that you could expect to see on the test. Okay, give me a second here to see if anyone has any questions. All right. All right, starting with the calculus stuff. All right, so, well, can't see that. Hold on. Sorry, 1 second. There we go. So, the calculus stuff, it's not so much that I actually wanted you to do differentiation and stuff like that on the test, but I do want you to see that the exponential decays and also the oscillations for an LC circuit are due to differential equations, which you can set up by just making use of potential drops across the various components. Okay, now there were 3 circuits that I did there, and I only did the discharging, although the charging also works. Okay, and so basically my question is, what is the differential equation for an RC, an RL, and an LC circuit? Okay, so for the RC circuit, this is where you have a resistor and a capacitor in series. The differential equation turns out to be, let me move this over to the side a bit. There, you can see that. Okay, turns out to be this right here. Okay, that's a differential equation. And you go, well, where did that differential equation come from? How did you get that? So one of them is on the one side, the dq by dt. If you unpack the tau, which is equal to RC, the dq by dt is basically R times I. Okay, and so that's the potential drop across the resistor. Okay, so the potential drop across the resistor, that's the left-hand side, that's got to equal the negative of the potential drop across the capacitor, and that's the right-hand side of this equation. Okay, so you don't have to, I don't want to go through that argument again because that's in the in that lecture there. But given this differential equation, okay, what kind of a solution can you expect? And the fact that this is a first-order differential equation, in other words, you're just differentiating, you have Q on both sides, So there's Q here and there's Q here. You're differentiating Q on the left-hand side once. This means it's a first order differential equation, okay? So you say to yourself, well, what function can I differentiate once and I get the function back again? And the answer is an exponential. Okay, if you take an exponential like this and you differentiate it, you get the exponential back. Okay, so in answer to the question, what are the differential equations for an RC circuit? We'll do that first. For the RC circuit, it's this one. It's dq by dt is equal to minus q divided by tau, where tau is equal to RC, the time constant. And what does its solution look like? Because it's a first order differential equation, because it's dq by dt on the one side and just q on the other side, your answer is going to be an exponential. Now, there's two ways that an exponential can form. One is exponential decay, and that's this one right here. Okay, that's the discharging, like the example I did above. And the other one is charging up, and that's this one right here. Okay, so I didn't show you that why this one actually solves that differential equation also, but it's very easy, because if you differentiate just the q naught, that extra constant in front, it just drops out. Okay, so basically, first order differential equation, you get an exponential in minus t over tau. Now, what about the RL circuit? For the RL circuit, the differential equation looks like this. And if you remember when I did the RC circuit above and the LC circuit below after it, the two equations look very similar, except that where you had Q in one, you replaced it with I in the other. So mathematically, these are the same, except your symbols changed. Okay, of course, the physical interpretation is different. I is the current, whereas Q is the charge, but it's got the same mathematical form. And tau here, it's not RC, it's tau is L divided by R. Okay, so what's the solution to this differential equation? Well, it's again basically an exponential in minus t over tau. Okay, so either you're going to have the initial current multiplied by e to the minus t over tau, or you're going to have the initial current multiplied by 1 minus e to the minus t over tau. Again, I didn't show this, but it's really simple. If you just plug that back in there, this extra term, the I naught term, when you differentiate a constant, what do you get? 0. Okay, so it just drops out. Okay, so again, first order differential equation, and you're going to get an exponential. It's the LC circuit that is different, and that's kind of why I wanted to, one of the things I wanted to highlight in doing this. In the LC circuit, it's actually a second order differential equation, which means that on the one side you have Q, there it is there. Let me isolate it a little bit better. So on the right hand side you just have the function Q. On the left hand side you have the function Q, but what? Differentiated twice. See that right there? So it's Q, but you're going to differentiate it twice with respect to time. So the question now is, what function can you differentiate twice and get the same function back again? And this time it's not an exponential. It's basically either a sine or a cosine. Okay, and so for the LC circuit, this is like the one where you have like radios, where you can make like an oscillating circuit where the current goes one way and then it turns around and goes the other way, and it just oscillates back and forth forever. Okay, that's how radios work. There's a certain frequency at which that oscillation occurs, and you can use that to tune into so your favorite radio station or whatever. Okay, the analysis there showed that you had a second order differential equation, and so you have this Q and you want to differentiate it twice with respect to time and get Q back, and the only functions that do that are sinusoidal functions, like the cosine here or the sine. Okay, now in my lecture I only did the cosine, but when you differentiate a sine twice, you're going to get back a sine, because every time you differentiate a sine you get a cosine, every time you differentiate a cosine you have a sine. So if you start from sine you'll get sine, cosine, sine. If you start from cosine you'll get cosine, sine, cosine. Okay, so basically it's any sinusoidal function. All right, so this is not really questions, but I could see, do you understand this? Okay, do you understand that a first order differential equation, your solution has to be exponential? Okay, either exponential growth or exponential decay. And for a second order differential equation, like the one that's appropriate for the LC circuit, do you know that in those cases you're going to have sinusoidal oscillations in Q. Okay, so that's it for the extra calculus bit. It's in the structure. Those questions are in the structure of multiple choice. So I'm going to basically say which equation is appropriate for what. So if you know the information that I just gave you and some of the details that were in the lecture itself on exponential decay, then you should do fine on those questions. Okay, let me see if there's any questions in the chat, and if not, we're down to two people watching. Okay, I think that's it for the stream. I mean, we went for 2 hours straight, so this is a pretty long stream. I hope I doubt people will watch it solid, but you can jump around in these streams. If you rewatch it, you can rewatch sections of it, and or you can rewatch them at twice speed. If you can absorb the information that fast. Okay, so that's it for the review. I'm going to be around on office hours if you have questions on some of the other types of questions that I didn't ask or that I didn't do during the stream. You can ask me then. All right, let me say goodbye to everyone then. Bye bye.